we present a method for multi-level stroke control and neural style transfer. Our method can be interactively applied and edited on mobile devices. In the following, we will first motivate and demonstrate our results using our app prototype, and then give an overview of the technical approach. Current applications for mobile neural style transfer are almost always one-click solutions. Users have no control over perceptual elements of the style, such as the stroke placement or the style granularity. This, however, limits artistic freedom and the ability to locally retouch style transfer results. We present StyleTune, a mobile app for interactive style transfer enhancement. Using our approach, the transferred stroke size and orientation can be interactively edited both on a global and local level. Notice how the mosaic tiles from the Delaney style are rescaled using the style granularity slider. Using the same network, also the stroke orientation can be edited on a global level. These elements can be freely adjusted in a continuous manner. Furthermore, our network architecture enables stroke size edits on a local level. Using different stroke granularities yields a visually more pleasing result. Less intrusive lines for the person and the mountains will make them stand out from the background. The different stroke edits will then be merged in feature space for a natural-looking transition between stroke scales. In a final step, the result quality and resolution can be greatly enhanced using a patch-based style transfer that can transfer even fine-grained details such as paint bristles and canvas structure. We propose a novel stroke adaptive style transfer network that enables interactive control over stroke size, intensity, and stroke orientation, all using a single neural network. To keep this network as lightweight as possible to allow an interactive experience on mobile devices, we map the different parameters to different input modalities of the network, which we will present in the following. Fundamentally, in feed-forward style transfer, stroke sizes in the generated image are dependent on the resolution of the input image, as networks produce stroke features at a certain scale dependent on the receptive field of the network. Thus, smaller images like the one on the left forwarded through the same network will contain larger strokes than the image on the right, as the receptive field of convolutional units in the network is larger for the left image. We make use of this property by introducing a novel two-stream architecture, where one branch is dynamically resizable to control the receptive field size. This style branch is responsible for stylizing the input. Here, the stroke scale factor, lambda s, that controls the size of the strokes in the output thus actually controls the downsampling factor for the input. Features obtained from the low-resolution style branch are then upsampled back to the original resolution. To retain image sharpness in the output, a second branch extracts high-frequency information from the high-resolution image. Both branches are merged and jointly decoded to generate the output image. As we increase the scale of the input image to the style branch, the stroke scale in the output decreases. Intensity of strokes is another important factor in style element control. For intensity control, we make use of conditional instance normalization. In regular instance normalization, the alpha and beta parameters are used to normalize and transform input features and are learned by the network. However, in conditional instance normalization, they are predicted externally. We predict alpha and beta from the stroke intensity factor lambda I and also use this factor to weight the style loss of the network during training. By training this mapping between style intensity factor and style loss, we can control the stroke intensity in a continuous manner. This intensity controls sharpness and saliency of strokes visible in the image. Finally, the third mode of control, which is stroke orientation, can be achieved by using the fact that convolutional neural networks are not invariant against rotations of the input. To produce oriented strokes in the output, we thus rotate the input image and then inverse the rotation of the output, which in return orients strokes by the chosen input angle. This relatively simple, but yet powerful method of controlling orientation is agnostic of the network architecture and can be applied to any feed-forward neural style transfer network without further modifications. To enable an interactive local editing pipeline for neural style transfers, we integrated our network and the mobile app in several stages. First, optionally, the content is rotated by a certain degree if stroke orientation is to be changed. Then, stroke features for different stroke granularities are pre-computed. When a user starts locally retouching results, a spatial mask is created, which can be used to blend together these stroke granularities to form an output image. However, as merging features and decoding takes time, we generate a real-time preview of the result. For this, intermediate images for each scale are computed from the previously generated features and blended together in image space in real time when the user retouches parts of the image. For seamless transitions between different stroke scales, the stroke features can be merged and jointly decoded to form the output image, which can then be exported or edited further. In a final step, the app can perform a high-resolution style-guided upsampling of the output using a service-based implementation of patch-based neural style transfer. Thank you for watching, and for more details, please check out the paper.